Hello students, welcome to today's session. In this session, we'll focus on the effects of feedback in control system. So in this lecture, we are going to explore a very important topic in control system, that is the effect of feedback. So as you know, feedback plays a critical role in determining how the system behaves, whether it's improving accuracy, reducing sensitivity, or enhancing the stability. Feedback can significantly influence overall system performance. So today we will focus on understanding these effects in a more structured way. So we will start from the effect of gain, then the sensitivity, and finally we will see the effect of feedback on the stability. So let's start. So for all of our discussion, we will consider a negative feedback system. To see the negative feedback system, here we have a block diagram. So in this block diagram, we can observe that the feedback path with gain h, that is the output taken to the input side with a gain of h, is having a negative sign. That's why it is known as a negative feedback system. So the overall transfer function can be defined as a Laplace transform of output, that is Cs, divided by Laplace transform of input, that is Rs. And it is defined as the G upon 1 plus Gh. So G, that is in numerator, is forward path gain. The denominator is having 1 plus Gh, that is the 1 plus multiplication of forward path gain and feedback path gain. So let's say if we don't have the feedback in the system, that is h is equal to 0, at that time the gain will be g, and if we have a feedback in the system, let's say h, then the gain is g upon 1 plus gh. So now we can see if we increase the value of h, that means we are increasing the value of feedback element, then the denominator, that is 1 plus gh, that will also increase. That means overall transfer function that will decrease. And so if we decrease the value of h, then denominator term, that is 1 plus gh, that will decrease. That means the overall transfer function that will increase. So by having feedback element, we can increase or decrease the transfer function gain. So let's take one example. So let's say if we have a forward path gain g is equal to 10, the feedback path gain h is equal to 0.1, then the gain without the feedback, that is g, it will be equal to 10, and the gain with the feedback will be 5. So from here we can see that the gain of the system because of the feedback path is decreased. Now, let's look at the effect of feedback on sensitivity. So the sensitivity is defined as the rate of change of output with respect to the rate of change of input. So in other words, it tells us how much the system output will vary or change if the input of the system parameters are slightly altered or slightly changed. So in control system, especially those involving negative feedback, we use the closed loop transfer function as Cs upon Rs is equal to G upon 1 plus GSHS, and this complete transfer function can be denoted as Ts. So the sensitivity can be defined as percentage change in overall gain of the system divided by percentage change in G. So it can be defined as the dt by t in the numerator divided by dg by g, that is the change in for percentage change in forward path gain. So the overall formula for the sensitivity will be S is equal to dt by dg multiplied by g by t. So now if we uh, reduce the formula for the sensitivity, so from the transfer function we have Cs upon Rs is equal to G upon 1 plus GH, or T is equal to G upon 1 plus GH. So from here we can get the ratio of G and t, that is g by t is equal to 1 plus gh. So if we differentiate it with respect to g, that means if we differentiate the overall transfer function t with respect to g, we will get as 1 upon 1 plus gh whole square, and that is the component that we will further take on. So further, if we proceed to deduce the formula for the sensitivity S, we'll get the formula for the sensitivity as 1 upon 1 plus gh, and it is very much resemble with the transfer function formula. So for negative feedback, transfer function formula is defined as g upon 1 plus gh, whereas the sensitivity is defined as 1 upon 1 plus gh. So now if we observe that as we increase the feedback path gain, that is h, the multiplication term, that is gh, will also increase, so as the denominator term will increase. And as the denominator will increase, the sensitivity, the overall ratio will decrease. So we can say that the sensitivity is actually inversely proportional to the feedback. So now let's look at the effect of feedback on system stability. So again, a negative feedback example. So the closed loop transfer function Ts can be defined as the ratio of output and input, that is g upon 1 plus gh. So now when we introduce the feedback in denominator, so the denominator becomes 1 plus gh. So let's say the feedback term we have taken 0. That means without the feedback, the transfer function will be g, that is the forward path gain only. And if the process is stable, is well defined, then without the feedback, the overall system will be stable. Whereas, let's say if we have the feedback path gain as h, then the denominator will be 1 plus gh. And let's say if we take the feedback path gain as minus 1 upon g, then the denominator term will become 0. And as soon as the denominator term will become 0, this overall system, the overall transfer function will become infinite and the system becomes unstable. So this actually makes the transfer function go to infinity, which means the system becomes unstable. So we can say that stability depends on the feedback element h. While feedback can improve the performance, it can also destabilize the system if not properly designed. Therefore, we have to be very careful while selecting the feedback element. So now if we summarize today's session, we saw that feedback plays a key role in shaping system behavior. It reduces overall gain, but allows us to control it more precisely. It decreases sensitivity, making the system less affected by change in parameters, and it can improve stability also, but only if designed properly. Otherwise, it can lead to instability. So, feedback adds intelligence and robustness to the control system, especially in critical applications like biomedical devices or biomedical system designs. So, thank you for your attention.